Now, moving to a slightly different topic, we are going to be talking from here on out about composite processing. Mainly processing of, we will start with processing of polymer composites, then we will talk about processing of ceramic and metal matrix composites. Okay, so different formats, different manufacturing processes, etc., etc. So the most common processes are related to resin matrix composites or polymer matrix composites. And in this case, the properties are basically controlled by the molecular chains inside the matrix. And these polymer chains can be primarily four different kinds. They could be linear, they could be branched, they could be cross-linked, and they could be ladder. So depending upon the type of molecular chain, you can have different kinds of properties. So if you had a polymer matrix composite, its properties are going to be defined by the temperature at which it can be used. So essentially, you have a change in the structure of the matrix, structure of the resin or the matrix beyond a certain point. And that first point is called the glass transition temperature. Beyond that, it, it could be either a semicrystalline polymer or an amorphous polymer. And beyond a certain point, it starts melting and becoming liquid. Now, it doesn't happen in all the cases, but in most cases it happens like that. So, what is the temperature at which it can, below which it can really be used? That is the glass transition temperature. So, if you had different kinds of polymer chains, so if it is amorphous, it's a jumbled up set of bonds, and if it is semicrystalline, you have some reasonable amount of short range order, but beyond which it is all jumbled up beyond that. Okay, so the first case is called amorphous, second phase is called semicrystalline. So many of these types of resins and the matrices that they result in can be described in terms of the type of bonds that they will result in. The most common type of resin that is used for polymer matrix composites is the polyester resin. There are two types of uh, polyester resins. The first kind is unsaturated polyester or thermoset polyester, and these are most commonly used for thermosetting composites, where for mainly for the applications are mainly for in the field of transportation, like boats, corrugated sheets, golf carts, etc. And the major reason for us to use this resin system is its low cost, because it costs 25% less than vinyl esters and about 50% less than epoxies. Epoxies are again some of the most common resin systems used for composites, polymer matrix composites. So, what are some of the advantages of some of these resins? Is that mainly cost. The second kind of resin system or matrix system that is used is phenolic. And especially if you want low cost, good insulation properties and mechanical properties, good high temperature properties, then you use phenolics. And the most common kind is done by the polymerization of a phenol and formaldehyde. Not the best um, kind of chemical structure or chemical nature that you want, but they have some really fantastic properties. These are used for mainly for general purpose compounds, and you can use them by adding wood floor to increase the impact resistance. If you want really high impact strength, then you add cellulose and glass fibers to phenolic resins. And if you want highly insulating type of compounds, then you can fill them with mica. You can also add carbon black to get heat resistant compounds, etc. So they have a number of different applications like wiring devices, auto transmission parts, lamination, adhesives, shell molding, etc. But essentially, anywhere you want really high temperature resistance is where you use phenolics. The most common kind and the most widely used are epoxy resins. So, what is the essential feature of an epoxy resin? It is that it has got very good adhesion, chemical resistance, and mechanical properties. So, essentially, you have an epoxide group which is a CH2 group with OCH attached to it, and they are linked to different kinds of ingredients. And the advantage is that they have very high molecular mobility, and when you cure them, you can cure them almost at room temperature. They have very low shrinkage during the hardening, whereas in the case of phenolics, there is a lot of water and other gases being formed, so they are not the best while you are during the curing. And in the case of epoxy resins, they have a number of different applications, aerospace, etc., etc. So, if you had um, additives added to that, you can actually increase the toughness of these materials. So, here is a um, representation of toughness versus percent carboxyl terminated butadiene acrylonitrile. So you can see that even at 6% you have almost 3 times the fracture toughness. Now something to note here is that these toughness values are pretty low, but uh, they are much better than many of the other types of resin systems and matrix systems that you can see in regular use. So going back to the traditional polyesters, what is a traditional polyester? They are unsaturated polyesters. They have an essentially you are blending an organic acid with an alcohol. When you heat it up, then what happens is that one H atom and the OH atom from this mixture combine to form water, and then you end up with the ester linkage here, RCOO OR prime. So that is the standard feature of an ester group. They have low viscosity and they can be reinforced with low viscosity materials. The advantage is that you can spray them, you can put them in open molds and things like that. So you can use them to process many small parts. You can also do compression molding, and there are many applications. So these are some of the most commonly used matrix systems, resin matrix systems for composite materials in real applications. So, what are some of the advantages of polyester thermosets? It is that you can easily mold them. That, I mean, more than curing, I think that's the biggest advantage. You can mold them into any shape and form that you want. And you have a wide range of properties, and there is tremendous amount of data that is available for these materials that can be used for developing applications and design parameters. And of course, they can be cured very easily. But there are some disadvantages, and I think most of the disadvantages are that they have poor durability, but more important than anything else, they can create tremendous amounts of air pollution issues. So you have to have an extremely clean working place in order for you to use these materials for making components. But the advantages outweigh the disadvantages because it is the first resin of choice for most composite applications, most common composite applications. So the is first step in polyester resin is polymerization. It is done in large chemical plants, and it is put together by manufacturers and sold in bulk. But when you are actually making the component, you have to cross link it and cure it. So this is done only at the time of molding, and it is done in the presence of reinforcements. So how is polymerization done in the case of polyesters? You have to take two monomers, and at least two monomers must be present, and each of those monomers must have two functional ends, and they will react with each other and form a linking entity that joins them together. And it is a byproduct as a result of condensation. So you have a polyester ester group, which are the links of these materials. So this one is a polymerization reaction that takes place in a big container or vat, and it is done in companies only making these polyester resins. So most of the time we don't even see this process. So you get the resin and then you use it directly in your composite manufacturing process. But this is also part of the entire process. So here is a list of different matrix and things like that. I mean, this will actually come later, so I will go over this one. Go over this one later. So this is the repeat of the previous previous slide. So what kind of properties can you expect to get out of polyesters? It is highly dependent on the nature of the matrix and not on the reinforcement. And higher molecular weight usually results in higher strength, stiffness, toughness, hardness, abrasion resistance, etc. Reinforcements are more important than matrix only for mechanical properties, but your other properties, other physical properties are all going to be dependent on the matrix properties. So why do we talk about melting point in polymers? There is really no specific melting point for polymers, especially when they are amorphous. But there is a temperature at which the material can be treated like a liquid for molding processes. So most of the time, um, you do not have any kind of melting point for these composite materials. you can say that melting point is really the temperature at which material becomes liquid-like. Glass transition temperature, on the other hand, is more important for most composite materials because that it becomes a rubbery type of a material above this glass transition temperature. It is solid but still pliable. So essentially you are saying that it is leathery above this temperature. So let me stop here and continue on the next section after this.